Bismillahirrahmanirrahim. This is the lecture number 18. No, this is the second phase of the. This is the second phase of the course. This would be about the wave propagation in elastic solids. Now, to start this, we should have some basic definitions related with the waves, such as what is wave, what is crust, what is trough, what is displacement, amplitude, frequency, wave number, wavelength, time period, propagation vector, polarization vector. These two are the propagation vector and polarization vectors related with the wave. Now, you have to study all these basic definitions and all other definitions which I did not write here related with the waves from your previous study, from anywhere by using any book. That would review your basic of the wave. Now, these are the two basic unit vectors, propagation vectors and polarization vectors. These are related with the waves, and we know that there are two types of basic waves, which one is longitudinal and other is transverse or shear waves, and sometimes longitudinal we say compressional waves or compression waves. Now, what is propagation vector? This is a vector which specifies the direction in which a wave travels. That this vector gives the direction of the wave in which your wave will travel, and this is called propagation vector. And what is the polarization vector? This is a vector which specifies the direction in which the displacement is taking place. This displacement is taking place in the direction, and that direction is specified with the help of a vector which is called polarization vector. These two are the unit vectors, and with the help of these two unit vectors we have two basic waves, which one is longitudinal and other is transverse. And what is longitudinal wave? Longitudinal wave when both polarization and propagation are in the same direction, then we say that we have longitudinal wave. And they are perpendicular with each other, then we have transverse wave or shear wave. No, to study the propagation of wave in elastic solid, we first start with from the equation of motion for displacement. We know that when we have equilibrium we have this type of equation. If we remember, we have studied it: partial Tij partial xj plus tau fi equals to 0. Now, what is T is the stress. This is the body force. This denotes the body force, and this is from the surface force. Now, if the continuum is not equilibrium, then we can write this. That on your right side will be balanced with this acceleration. This is the same when you have equation F is equal to ma. So we know that Tij equals to Cij KL SKL, and S means strain SKL. SKL will equal to this. This is the displacement U. Then we have Tij equals to 1 by 2 Cij KL partial UK partial XL plus partial UL partial XK. Now you can write this as, and we know that I and J, they are free indices, and K and L, they are dummy indices. So you can change the dummy indices either in this term or in this term. So we have changed the dummy indices here. We can write it as, it is partial UL partial XK, and this is Cij LK. And we know that our stressed elasticity tensor C is symmetric in last pair. So you can write Cij LK equals to Cij KL. So this is this, and no, these are same, so they are 2 times. So you have Tij equals to Cij KL partial UL partial XK or partial UK partial XL. No, use this equation in equation of 1 and ignore the body force term rho Fi. Then you have this. This is the constant, and you can write partial square UL partial XJ partial XK equals to this equation number. This is equation number 2, and this is the equation of motion for displacement. This is the equation for displacement. And what is displacement? U is the displacement, and it has components U1, U2 and U3. And you can see that J, K and L, they are dummy indices in equation number 2, and I is free. So you have 3 set of equations from equation number 2, U1, U2 and U3. These are components of displacement. And this is the partial differential equation. So let us assume its solution in this form. U is equal to, no, this solution is basically in the form of a plane wave. Why it is a plane wave? This is basically equation number 3 is the representation of the plane wave, displacement of the plane wave. That U is equal to, U is displacement equals to f of x dot n minus vt, and this is p. No, keep in mind that what we have written, n is propagation vector, p is polarization vector. So throughout the whole course, from up to now, from now to onward, we will use n, small n for propagation vector and small p for polarization vector. And these are 2 unit vectors, n is unit vector and p is also unit vector. So remember these 2 notations, don't mix these. And what is v? V is the phase speed of the wave, t is the time, and x denotes the position vector of any particle which moves with the wave. Like that, when you have sinusoidal wave, then any point on the curve whose position vector from the origin, that is denoted by x. No, x dot n is basically a constant which describes a plane normal to the unit vector n. Now if you remember the equation of plane, what is that? An equation passing equation of plane passing through a point x1, x2, x3 is that a into x minus x1 plus b into x minus x2 plus c into x minus x3 equals to 0, and you can write that ax plus bx plus cy equals to ax1 plus bx1 plus ax1 plus bx2 plus cx3, and this is the d, this is that constant, and on left side you have x dot n, x1 xyz, this is any point on the plane, and x1 x2 x3 in this point plane is passing through this point x1 x2 and x3. And what is abc? These are the components of your normal in that plane. This is exactly the same, that can be written also x dot any normal whose components are abc equals to constant d. This is there, that is why we are saying that this is the representation of plane wave, that we have constant involved in the solution, and that constant describes a plane normal to this vector x dot n. Now what we have to do, we have supposed this type of solution. Now we will use this solution in equation number 2. As we are saying that this is the solution of equation number 2, here we have written let us assume a solution. It means that we are taking a solution of this equation number 2. Supposing in PDs we usually suppose the solution, then we use that solution in equation in the PD. So we will use this solution in equation number 2. So to use this type of solution in equation number 2, we must have these type of partial derivatives of equation number 3. So you can write your solution 3 in this form: ul equals to f of these are the xi and ni, x dot n and pl. This is any nth component of the solution. So partial ul partial xj would be f dash xi ni minus vt, pl here would be nj. Simply derivative of this with respect to xj, and that will be partial xi partial xj, and that would be delta ij ni, and delta ij ni will give you nj. Now you are using here the basics which you have learned in your first phase, lecture number 1, 2, 3, I think, that delta ij ni will give you nj. That you can open summation on I, that would be delta 1 j n1 plus delta 2j n2 plus delta 3j n3. No, if j is 1 then you will have n1, if j is 2 then you will have n2, if j is 3 then you will have n3. So in general it would be nj. This is the second derivative. Again you have nk. F dash nj and f double dash nj nk. Now for t, again you have f double dash xm nm minus vt and v square pi. Why we have written here I? Because we need I, because we have I on the right hand side of equation number 2. You can see here, you can see here on left hand side we have partial derivative of ul with respect to xj and xk, and on right hand side you have partial derivative of ui with respect to t. So we need first to change L into I, ui. Here again, here will be also I, and to avoid the overlapping of indices, we have changed I to m. So here would be xm nm vt. Now this is the partial square ui partial t square is equal to f double dash this v square pi. Now use all this in your equation number 2. What we have? We have this on left hand side, this thing equals to rho this thing on right hand side. These are cancelled with f double dash, and we are left withCijkl njnkpl equals to rho v square pi. Now here we will define a tensor with the help of this, with the help of these three, C, Ni, Nj and Nk. So you can write this product of these three as gamma IL. We also call this as propagation tensors. In literature, some book use its name as propagation tensor, gamma. This is second order tensor. No, this is your exercise to prove that this is a tensor, and this satisfies a tensor of a transformation law of second order tensor. Now you have to prove it. Now when you will use this, here you will have gamma IL PL equals to rho v square pi, and this equation is called Christoffel equation. This is Christoffel equation. Now if you compare this Christoffel equation and your known equation, you can see that this is something like Ax equal to lambda x, p here, this is lambda, this is your matrix, this is second order tensor, and you know that we have a matrix 3 by 3 matrix corresponding to second order tensor. So this corresponds to matrix A, this is vector, and this is your eigenvalue, and this is again your vector Ax equal to lambda x, eigenvector x for eigenvalue lambda. This is called Christoffel equation. No, pi is, what is pi? Principal direction of gamma IL. Principal direction is basically the eigenvector unit. This is unit eigenvector because we have started from the unit eigenvector, and we say this is principal direction. Eigenvector, principal direction of gamma IL, eigenvector of the matrix representing gamma IL. Eigenvector of the matrix representing gamma IL. Now what is the corresponding eigenvalue? This rho v square, this rho v square, A x equals to lambda x. This is the principal values of gamma IL. which is basically the eigenvalues of the matrix representing this. These are the eigenvector represent of the matrix representing this gamma IL. These are the eigenvalues of the matrix representing this gamma IL. In further study, we will make use of this tensor to study the waves in isotropic and anisotropic material. Now let us check first its symmetry, either it is symmetric or not. Now, this is definition: gamma IL equals to CIJKL NJ NK. If gamma IL equals to gamma LI, then we see that this is symmetric. So to check this, what we will do, we will simply interchange I and L with each other. I L left side, similarly on right hand side. I L L, CIJKL, I and L, NJ NK. Now apply the pairwise symmetry of C, that this C should be equal to CKI LJ, this is NJ NK. Now here what we have done, we have simply interchanged I and K. Why? Here we are using symmetry in first pair, that CKI LJ equals to CIK LJ. Again here we will use the symmetry in second pair, that is CIK LJ equals to CIK JL. No, we will interchange J and K with each other. It would be CIJKL and here would be NK and NJ. We can interchange these because J and K, they are dummy, so we can write K instead of J and J instead of K. So it would be this CIJKL NK NJ, and this is, you can write this, and this is your gamma IL. And you can see that gamma LI equals to gamma IL. So it means that this tensor is a symmetric tensor. This is a symmetric tensor. This is the lecture for this is the first lecture for the phase 1, and in further lectures we will discuss the propagation of waves in isotropic and anisotropic material with the help of this tensor gamma, that we will suppose the direction of n, then we will take that direction similar with the direction of axis of symmetry of some particular material, and use the result of these constants from the matrix C. Then again we will write this gamma matrix for this this tensor. Then we will calculate its eigenvalues and we will define the waves in that isotropic material. We will see that how we will do that thing. This is the end of today's lecture. Thank you so much.